Okay, this is video number 2 of Introduction to PSPICE. We're going to continue looking at our resistor circuit and performing a DC analysis of this circuit. I mentioned in video 1, I referenced some things in the book using the abbreviations for scaling factors. We use the little m for the 5 milliamp current source. That is on page 4 of the textbook, and we're going to be going through the example on page 6 as we move along. Section 1.3 of the textbook on DC analysis. So here we have our circuit, which we built in the first video. What we're going to do now is a DC analysis, otherwise known as the bias point calculation. So what we're going to do is, what we have to do a simulation is to first, we can click on this box right here and create a new simulation profile. We can choose any name we like, called DC analysis. And when we do that, if you look down at the bottom, across the toolbar, you see down here I have this flashing icon here telling me that a window has opened. And when I pull that up, it gives me all the different options for doing an analysis. You go to analysis type, and you can see we have 4 different types of analysis that we can do. Time domain transient analysis, similar to how we ended circuits 1, looking at a circuit's response to changes, voltage or current. We can do a DC sweep, which we'll look at that. We'll look at all of these eventually. But to do a DC analysis, where we just want to find all the voltages and currents in this circuit here, we want to do a bias point analysis. And so the general settings for the bias point, we can do detailed bias point analysis. Actually, we're not going to do this. We're not going to do a sensitivity analysis. What that would do is we can take any one of these parameters and we can say, what are the voltages and currents in this circuit if we change this resistance by plus or minus 10%. So we're going to look at the sensitivity of the circuit to varying component values. We're not going to do that one now. We will look at small signal gain towards the end of our study of PSPICE, but for right now, we're not going to make any more changes. So we'll go ahead and apply those simulation settings, hit OK, and we are now ready to simulate the circuit. So all we do is click the green Run button, and we'll start to execute the simulation. And let me show you what popped up was a window right behind this one. Came out pretty large. Right now it's blank. And in here was the result of my simulation. Didn't tell me there were any errors. Calculated the bias point was calculated, simulation complete. Now, there isn't anything else obvious except so what we need to do now, we can look at the voltages and the currents in the circuit by clicking on these radio buttons. These are the items that become available to us because we did the bias point analysis. So we can click on any one of these or all of these at the same time. Click on the voltage, and we're getting the voltage at every node. And you can move these boxes around. This node is 24 volts. Right here, anywhere along this rail is 22.6. Here's 48.4. Whoops. And 12 volts is right here. Of course, 0 volts anywhere along this rail is 0 volts. We can look at the currents simply by clicking on I. And here you see that the current through this branch is 263 microamps, 2.8 milliamps here, of course 5 milliamps through this branch, 2.5 2.57 milliamps here, 2.4 milliamps here, and so forth. Okay? So it's really that simple. So we can do any kind of simple circuit from the introductory chapters of circuits 1, DC circuits, very simple to do. We've done all the analysis by hand, and now we can see how simple it is to do using PSPICE. Okay, so everything that I'm presenting on these videos can be found in the slides as PDFs as well. So you can either, when you finish watching the video, refer back to the video or refer back to these slides to see how we're doing these circuits here. So let's go ahead and move on. The next thing we're going to do is look at a circuit that has a dependent source and perform a DC analysis looking at the dependent source. Now the dependent sources, which we learned about in circuits 1, are these triangles. And in this particular circuit here, you can see that this source is a current source that's dependent on the voltage Vx, which is the voltage across this resistor here, this 2 kilo ohm resistor. So we have a 1 millivolt source, voltage source applied to this resistor circuit here. The voltage across the 2 kilo ohm resistor is used to create a current in this branch, which will flow through this resistor circuit over here. So in PSPICE we have 4 different types of dependent current sources, dependent sources, 2 current sources, and 2 voltage sources. Each one of them has a different letter in the PSPICE library, and here in the book it tells you where you can find these sources in the analog library. So let's go ahead and build this circuit in PSPICE using the voltage controlled current source. So let's go ahead and create a new project and call it DC Depend. Again, analog or mixed AD. Blank project. We have our blank template. And let's go to analog and start placing resistors. We want to use the voltage controlled current source, which uses the G symbol. We'll zoom in on that, take a look at how we want to connect it, and go from there. Let's find the source. DC voltage source of 1 millivolt. Last, we need the ground symbol. And again, the one that I'm using is this 0/capsim. Has the number 0 there. The book specifically talks about a different way of placing ground, which actually requires you to edit the properties of the ground symbol and type in the number 0. And you don't actually have to do that in these later versions of PSPICE if you choose this particular ground. I'm going to clean this up a little bit so that I can zoom in. Alright, I wasn't able to get the whole circuit to fit on the screen at once, but I wanted to zoom in here and so we can take a look at our voltage controlled current source, and you can see that it has voltage probes on one end and a current source on the other end. So all we have to do is simply hook up wires properly. So let's go ahead and look up the circuit on this side. Change our voltage source to 1 millivolt. Alright, so what we need to do is we need to measure the voltage here across this resistor and apply it to the dependent source. So we'll just simply run a wire across each of the terminals of R4. Which the value of R4 is actually 2K. And this resistor here is 10K. These are both 1 kilo ohm. Now, to run the current through this portion of the circuit, we have to connect the current source in series. So the current has to flow through the current source through this resistor here. So we'll connect these up. Change our values. And make sure we get the gain right. This resistor value is 0.1K, 100K, 1K, we don't have to change that one, and this one is 20K. I just noticed that I may not have used the right one. Notice we had 2 current sources here. So back to analog. Find our G. So you have G and G poly. We wanted our gain in the circuit to be 10, so let's see if we can get this to work by changing that to 10 and see if that works. Alright, so I think our circuit is finished. So let's go ahead and save that. And now we need to create our simulation. Let's go ahead and do a DC analysis. So same as before. Again, the simulation profile shows up at the bottom. So I'll click on that. Bias point, OK. Go ahead and simulate the circuit. Bias point complete, and everything seemed to work. I do want to see some voltages here. There we go. This voltage when the panel was underneath this current panel. But the circuit is working the way it's supposed to. We have 1 millivolt coming in, very small amounts of current, nanoamps. And we have very large resistor values, current gain of 10. We actually call this not a current gain since our input is voltage and our output is current. We call this a transconductance gain. And you can see that our output voltage across R8 here is minus 76 volts. Everything seems to be working fine. Okay, so that ends video number 2, our final DC bias point analysis using dependent sources. In the next video, we will do a DC sweep, showing how a circuit will respond to DC sources that can change in their value, sweep over a certain range.